All right, as we move to section 10.2.2, we're going to talk about permutations. There are many kinds of counting problems. In this chapter, we'll learn to recognize problems that involve arrangements where order matters and others that do not. In some cases, outcomes will be repeated, but in others, they will not. So, for example 1, it says Jasper finally managed to hold on to some money long enough to open a savings account at a credit union. When he went to open the account manager told him he needed to select a 4-digit PIN, personal identification number. He also said that you could not repeat a digit, but you can use any of the digits 0 through 9 for any place in his 4-digit PIN. So how many PINs are possible? So if we go back and think about what we did last lesson, there are 4 different decisions he needs to make. And if you look at the numbers 0 through 9, that is actually 10 numbers. So he has 10 possible choices for the first digit. In this case, we can't repeat. So then we have 9, and 8, and then 7, because again, we cannot repeat any of our digits. So if we do 10 times 9 times 8 times 7, we get 5,040 ways. Notice the decision chart for this problem looks like the beginning of 10 factorial, but it does not go all the way down to 1. Factorials can be used to represent this problem, but you must compensate for the factors that you do not use. So we could write this as 10 factorial divided by 6 factorial. How does this method give you the same result as the decision chart? So remember what we did at the end of the period, or the end of the last lesson. 10 factorial means 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And since they're all separated by multiplication, the 6's, 5's, 4's, 3's, 2's, and 1's all cancel, and you're left with just 10 times 9 times 8 times 7, which is the same as 5,040, or the same exact thing that we got up here by doing the decision chart. All right, as we go to example 2, it says 25 art students submitted sculptures to be judged at the county fair. Awards will be given for the 6 best sculptures. You've been asked to be the judge. You must choose and arrange in order the best 6 sculptures. If you did this randomly, how many ways could you choose the 6 best? So again, I have to make 6 decisions here. Well, there's 25 art students, so 25 possible students could get in first. Whoever gets first can't get second, so there's only 24 for a second, and then 23, 22, 21, and 20. So if I multiply that all out, get a really large number, 1275, 12000. So 127,512,000 ways. Show how you simplify 25 factorial divided by 19 factorial. So remember, 25 factorial would be 25 times 24 times 23 times 22 times 21 times 20 times 19 times 18 all the way down to 1. And 19 factorial will be 19 times 18 times all the way down to 1. And like we said before, the 19 is going to cancel 18, those numbers in between, and all the way down to 1 will cancel. So we are left with 25 times 24 times 23 times 22 times 21 times 20, which is going to be the same answer. So then it says, where did the 19 come from in the original expression? How could you know the 19 from the numbers in the original problem? Why did 19 factorial in the denominator become an important step in coming up with this answer to the problem? So where is the 19 coming from? Well, the 19 is coming from the fact that there are 25 students and we are only choosing 6 of them. So the 19 is the ones that ultimately are not getting chosen. So we're taking the 25 minus the 6. So this is the total. This is the chosen. And that's how we're getting the 19. And this is an important number because that's how many we're canceling out only. We're canceling out everything from 19 down. So what we have here is we have a permutation. So what is a permutation? A permutation is an arrangement of objects, and objects can be anything, numbers, letters, people, arrangements of anything, where there's 2 things that are important here. One thing is that you cannot repeat, or objects are not repeated. So like here for this art project, whoever got first could not get second or third or any other position. We couldn't repeat the same project. And the other major important is that order matters. Again, going back to look at this art sculpture project, yeah, order matters. I'd rather have first place than second place or third place. I'd rather have second place than fifth place. So order matters in that case. And there are 2 ways that we can solve this problem. So as you can see, we were able to get our answers via a decision chart. So that's one way we can do a permutation, is we can still use a decision chart. But we can also use a formula. And that formula is going to look like this, NPR. So notice how the N and the R are kind of like subscripts. They're smaller letters, and then P is a regular size letter. And the formula is N factorial. So if you looked here, we did 25 factorial. 25 was the total number of people in the contest. And then the way we got the 19 was we took the total minus the number of chosen. And that's what N and R stands for. N is the total number of objects. And R is the number of chosen objects. So the bottom, again, we took the total minus the chosen to get to 19, is N minus R in parentheses, and then we take the factorial of that. So when do I use each one? Honestly, for a permutation, I usually use a decision chart. To me, it's just a little bit easier. However, I do sometimes use a permutation if I have a lot of numbers to choose from and I'm choosing a lot of objects. So like if I'm choosing like 15 objects, then I'd have to have 15 lines in my decision chart, which can get a lot to write and a lot to work with. So that's when I'd probably use the formula. But if I just have like 3 or 4 numbers to choose from, 3 or 4 decisions, then I usually use a decision chart. So it is important that you look at some examples of what are permutations and some things that are not permutations. So for example, these are examples of permutations. So it says all of the arrangements a child can make on a line on a refrigerator door with 3 magnets of A, B, and C. So again, for it to be a permutation, we have to have 2 things. Order matters, and we cannot repeat. So in this case, there's only 3 magnets, A, B, and C. So we can't repeat multiple A's or multiple B's or multiple C's. So there's no repeating. Then if we go to the other part where order matters, well, yeah, ABC is different than CAB. So again, order matters here. So we can say ABC different from CBA. For part B, all the 4-digit numbers you can use you can make using the 7 square tiles numbered 2 through 8. So again, since they're square tiles, there's no repeating. And since it's a number, 4-digit number, 2, 3, 4, 5 is different than 5, 4, 3, 2. So again, order matters. So those are the 2 criteria for permutations. For C, from a group of 8 candidates, 1 will become president, 1 vice president, 1 secretary of the school senate. So again, we're talking about people here. You can't repeat people. You're each your own individual self. There's 1 person president, 1 person vice president. So there's no repeating people. And yeah, order does matter because the job of the president is different than the job of the vice president, which is different than the job of the secretary. So order does matter in this case. So this is an example of a permutation as well. Here are some examples of non-permutations. So it says, and actually what we were supposed to do here is just find the total number of possible outcomes. So for this one, we would do 3 times 2 times 1, or 6. For this, we have 1, 2, 3, 4, 5, 6, 7. So 4 options. And there's 7. So 7 times 6 times 5 times 4. Or, again, if we want to look at the formula, we can do 7p4, which would be 7 factorial divided by 7 minus 4 factorial. Sorry, 7 minus 3 factorial. 7 minus 4 factorial, yes. So that would be the same as 7 factorial divided by 3 factorial. So that means the 3, 2, and 1 would all cancel, and it would be the same as 7 times 6 times 5 times 4, which is 840. And then for our last one, we have 3 slots. Again, 8 people could be president, 7 for vice president, and 6 for secretary. So if I do 8 times 7 times 6, we get 336. Again, if you wanted to use the permutation, I would have 8p3, which is 8 factorial divided by 8 minus 3 factorial, or 8 factorial divided by 5 factorial, which again would then get us to 8 times 7 times 6. For the non-permutations, again, we will explain why not, and then find the total number of outcomes. So D says all the possible 3-letter license plates using A, B, and C. Well, in license plates, we can repeat objects. There could be a license plate that goes AAB or CAC. So therefore, repeating aloud, that's why it's not a permutation. But to find our total number of outcomes, we can still use the decision chart, just we're going to repeat our letters. So we'd have 3 options for the first, 3 for the second, and 3 to the third. So we'd have 27 outcomes. So if you notice, the fact that we're not repeating here, we compared 27 for the non-permutation, 6 for the permutation. For letter E, 4-digit number you could write if you could choose any digit from the numbers 2, 3, 4, 5, 6, 7, 8. So here, for B, we had a square tiles only, but here we can just pick the numbers. So again, the fact that repeating is allowed here. So again, we're doing 4-digit numbers. So I have 4 decisions. I have 7 possibilities, so 7 times 7 times 7 times 7. 7 to the 4th. Which is 2,401. Then F, from a group of 8 candidates, 3 will be selected on the Spirit Committee. So, the whole point of this is if you're on the committee, you're on the committee. You're going to work together at all times and not necessarily have each person do a separate job. So this is the fact that order doesn't matter. And we'll talk about this case next lesson. So for right now, we don't know how many total possible outcomes there are.